start by compiling my codes. Doesn't throw an error, and I can also run my program without throwing an error. First, I'll provide examples of running programs in the background. So if I run sleep in the background, I can run commands like echo high or like list in the foreground. And if we wait for a little bit, we should get a message saying that our background process terminated. Now, when we ran the background process, we got a number, which we call a job ID, which just simply records how many processes are being ran in the background, and also the process ID of the background process that's running the command. Now, I'll provide an example of, for that, there's a few things to know about the background processes. Like echo high gives us an output in the foreground. And if we run it in the background, we also receive its output in the foreground. And if we run a command that throws an error in the foreground, the error is also reported in the foreground, even if it's run in the background. Next, I'll provide examples of running listing background programs. So if I run sleep 20, sleep 20, running 3, if I run the command ps, then it lists all the background processes that are currently being ran. And we can also send particular signals to these background processes. Like if I run a really long background process and I wanted to manually terminate it, wait, I'll just ignore it because there were dumb messages and I didn't want to complicate things. I can use the command kill and manually send this process ID 3189752 and terminate it, which instantaneously terminates the process. And this time I didn't add an extra argument of different signals that I wanted to send, so it defaulted to just simply terminating it. But I could add an extra argument, which is an integer, to send a particular signal to these background processes. Now I'll talk about the codes that enable us to do this. First function we need to look at is at line 227 of the mish.c. It's called execute background command. And it essentially forks the process, and in the child process, it executes the command. And in the parent process, notice that there aren't any wait calls. So it's essentially non-blocking. And that's what enables us to run other commands in the foreground while something is being executed in the background. But we still need to display the done message when the child process terminates. So how do we do that? Firstly, we have a global array that has structs that store information about these background processes. And this struct and this global array is defined in built-in.c. And the struct bg_job_t is defined in its header file. It stores the job ID, its process ID, the command that it's running, whether that's echo high or sleep 10, and also its status, whether it's currently being ran or not. And the function add_job is called whenever we have a new background process. And it simply creates the struct and adds it to this global array. And recall that when a child process terminates, the parent process receives a signal. So we have a signal handler for this. If we go back to mish.c, we have a signal handle called sigchild. And what it essentially does is called waitPID. Check if there has been a child process that terminated. We get its PID and call markJobDone. The implementation of this function is simply traversing through the global array that stores a struct and finds the corresponding struct, constructs the done message using the information that's stored in the struct, and then displays the message. Now I'm going to talk about alternative ways to implement this. Now, something that can't be changed is one, it needs to be non-blocking. So the parent process can't simply call wait. And also, we need to handle something when the parent process receives a signal that the child process terminated. But I don't think it's essential that we have this global array to store the information about the background process. In fact, in the execute command that forked the process to run a background process, I think we could have set up a pipe here between the parent process and the child process and store this pipe in the parent process. And before the child process executes, it could write to this pipe that it terminated and the essential information to construct the dump message, like the process ID and the job ID and the command that it was running. And the signal handler that's going to be ran in the parent process can read from the pipe and use these information to construct the dump message. So I think it's a trade-off between memory and runtime. My implementation stores the memory, so without reading the pipe, we can directly construct the dump message. So it's faster, but it's using more memory. The alternative way of writing the essential information to the pipe would run slower because it has the extra step of writing and reading from the pipe, but doesn't require any extra memory. The reason why I took my implementation is because the testing suite for this milestone had timeouts. So our background processes needed to execute in a certain amount of time. So in my scenario, the code running faster was more important than efficient use of memory. Next, I'll talk about how signals are handled. And that's just simply looking at the implementation of command kill in commands.c. It firstly checks whether a process ID is given. And it allows for a second argument, which is the signal that we want to send. And if that isn't given, we default to sigterm, which is just simply 15. And we use the system call kill. And the reason why the implementation of this command is rather simple is because the complicated calls that need to be made to control the operating system is abstracted by the system call kill. The alternative way is for us to create our own implementation of this function kill, but that will make the code a lot longer, and we're not using abstraction to our advantage. So that's why I resorted to using the system call. Next, I'll talk about the implementation of the server functionality. And that can be accomplished by looking at the command start server. So all these initial code is just preliminary setup to run the server. And the most important code is the loop that is this do loop. So each time we have a FD set of that contains a file descriptor that is used as a socket for the server, which we need to check for incoming connections. And we also keep adding file descriptor that are used as sockets for connecting with the client if there's a new connection. And the way we store these sockets for client is by using a linked list. And it's because we don't know how many linked new clients we're going to get. So we need to get ready for arbitrary many connections. Thus, we need a dynamic memory allocation. That's why we use a linked list. Now, in each of these do loop, we call select and see if there's any incoming connections or reads that we need to make from these file descriptors. If there's an incoming connection, we try to accept the connection using a helper function. After that, we traverse through the linked list, and for each of the client sockets, we see if there's anything to be read, and if there is, we traverse through the linked list again, and then we write to each of these sockets to echo the message that was received by the server. Now, because we allocate memory dynamically and also use file descriptors dynamically, we need to gracefully exit when the server is going to close. And for that, we use the function clean exit, which simply traverses through the linked list, frees all the memory that was being allocated, and also closes the file descriptor and file descriptors that were being used. But clients can abruptly disconnect from the server when the server is still running. And when that happens, we do remove it from our FD set so that we don't redundantly check these sockets. And we also close the sockets, the file descriptors, so that we don't run out of them. But we do not delete from the linked list. And the disadvantage of this implementation is that the linked list would keep getting longer. But there's an advantage to this implementation. And please consider the scenario where the server receives a signal to close down when it was in the middle of removing a particular client from the linked list. When the clean exit is then called abruptly during this process, we do not know the exact behavior of clean exit when it's handling this client node that was just being removed. I didn't want that ambiguity, so I decided to keep these client nodes in the linked list while the server was running so that everything could uniformly be handled when the server is all being closed. That is it for my final video walkthrough. Thank you.